get started with our very first talk. We have Federica Rossino from the University of Exeter. Federica, come on in.
Okay. Perfect. Okay. Let's get this started then. Hi everyone, my name is Fede and I'm originally from Italy, but I'm currently doing a PhD here at the University of Exeter. And we've heard a bit about planets. There's no planet B, planets' atmosphere, some are rocks, some are super gigantic and gaseous. But how do we actually find any of these exoplanets? We cannot simply just look out at the night sky and say there's one there. So today I'm going to be talking about two of the main ways we actually find any of these exoplanets. And let's begin with saying that to date, we have discovered more than 5,000 exoplanets. And the first exoplanets were only discovered about 25 years ago. So we're going fast, but there's so many out there. Actually, we believe that for every single star in the universe, there's at least a planet. So let's talk about the first way of detecting exoplanets. So this is called radial velocity. We all know that planets go around stars because of something called gravity. But gravity is a force that always has an opposite and equal reaction. So just as much as the planet is being pulled by the star's gravity and going around the star, so is the star also being pulled by the planet's gravity. But usually planets are much smaller than stars, so that the orbit that the stars have around the common center of mass, this center point here, is actually much smaller. If we look at a star edge on, we can see this wobbling back and forth. Now, we cannot really see a wobble per se in the sky, but what we can see is a wobble in the light. So what we do, we look very hard at the light emitted from these stars, and we look at its spectra, meaning its colors and its lines. And as you can see here, when the star moves left and right, these black lines, these absorption lines, also move back and forth. By measuring how much they wobble, we can figure out how big a planet is. A second way of finding exoplanets is called transit photometry. It literally just means that we look at the change of light intensity in the star. So when the planet comes in front of the star, it's going to block some of its light. And what we can see is overall light of the star, then planet comes in, there is a dip for as long as the planet is in front of the star, and then once the planets get out of the star's way, we get up and we get back to the star's normal intensity. And in these ways, we actually found most of the discovered planets. So these are our two main weapons to actually go out in the sky and say, there's a planet there. Thank you very much for listening.
Brilliant. And who's next? Brilliant. And that one, clip on your
Is this a clip on? I don't know how to put this on. Do I just slide it in? Can you help me? Awesome. Cool. Alrighty. Oh, hello? We're good? Alright. Hi, everyone. Thank you for being here on this rainy, misty day. The fun thing about rain and mist, I will say, is that they are processes that happen in our atmosphere. And if we want to study our atmosphere, the fun thing about this is that now we can study the atmospheres in other planets. So to give you a little bit of historical context, if we were to put the entire history of Earth in a calendar year, right before we're about to scream, Merry Christmas, Happy New Year, right about then, we would actually be discovering exoplanets for the first time ever. They were actually discovered in 1995. And the first atmosphere of an exoplanet was characterized not that long ago in the context of our whole history in 2001. But how the heck do we study exoplanet atmospheres? So the way that we do this, the previous speaker already showed what transit looks like, but as the planet passes in front of its star, we basically just point a telescope and stare at the star for as long as we can, and as the planet passes in front of the star, it will form this dip in brightness. It forms a shadow. We're seeing less of the star's light, so we see these dip in brightness. Now the fun thing is that we can actually do this through different filters. Oh.
Sorry.
Yep, no, you're good. So
We've lost power, so just keep going.
okay, yeah. So hopefully that visual was helpful. But as we look, basically as we look at the star's light dip through different filters, we can actually see what the atmosphere is made of. Because the fun thing about light is that it's like a fingerprint. So several light signatures that we see are going to tell us different things that the atmosphere might be made of. And basically, by measuring how deep that dip in brightness goes through different filters, we can actually extract or put models to our data that tells us what that atmosphere might be made of. Because the power went out, we also have a really nice demo over here if you want to get a better idea visually of how what's called transit spectroscopy works. But hopefully that was enough context to kind of give you an idea, how is it that we do the work that we do? There's a lot of exciting things that we're talking about, but how do we truly get these light signatures? It's basically, one of the ways is just staring at a star long enough and seeing those dip in brightness in different filters. Thank you. You're good. Oh, sorry. Oh, here you go.
Fantastic. So thank you for being really patient while we've lost power at the moment, but hopefully it's still coming through reasonably well on the live stream, and those of you can hear as well. Tobias is next. If you could come along. So if there's much point in holding these, but actually it is worthwhile for the live stream. So if you can click those on, I don't know which one does which. So we'll brilliant. I'm afraid you're going to have to act out your...
Okay. Hello, everyone. Yeah, as you can see on this very nice illustration, I am Tobias Meyer. I'm a postdoc at the University of Oxford, and I'm mostly interested in how rocks flow inside these planets. Yes, you heard that right. Rocks flow on very long time scales. They're not really they're not really molten. If we look at Earth, we have like a crust, we have a mantle, and then we have a core. And I'm interested in how the rocks flow inside the mantle. So we don't have the illustration here now, so maybe you just have to imagine I'm like in the mantle now, I'm rock. And here is the surface, and here we have the boundary towards the core, which is really hot. So if I'm here and I'm a rock, then I start to get really hot. And when I get hot, I get less dense, and then I start to move towards the surface. At the surface of the Earth, we have a lot of water, it gets cold, I become more dense again, and I start to move back down. And so that is called mantle convection, which is occurring inside Earth's mantle. And I'm mostly interested in whether mantle convection also occurs on planets that are very close in. Michael talked a bit about it, about these very hot planets that are very close into the star, and and that means that they always face the same side towards the star. So again, imagine now I'm like the day side of a planet. I'm like one side, and this is the sun. Then I would just move like this, and this means the day side, where it's always day on the planet, is really hot, and the other side, oh, perfect. So yeah, exactly. So then it moves, and then it is always showing the day side here towards the star, which is really hot. And for these planets, we have done these like mantle convection simulations, and I've found that then on that side, we see that on the day side actually, a lot of rocks will flow into the mantle on the day side of the planet. They will go around in the mantle, around the core, and then, yeah, and then move towards the night side of the planet. So on the night side of the planet, they become hotter again, and then they start to rise again on the other side. And yeah, so we know that for these planets, possibly we could have this mantle convection regime, but which is quite a bit different than what we have here on Earth or the other terrestrial planets we have in our solar system. And if you want to know more about that, please come and chat to me, and I can maybe show you the video on my phone or so. Thank you very much.
Thank you so much. So that's our last set of speakers now. We have one more round of speakers going on at past. So thank you so much for tuning in and for being tolerant of the technical issues we've had. We've lost power completely, but hopefully it's coming through on the live stream. If you want to hang around, handle some meteorites, chat to the astrophysicists, please do stick around, and we'll have our final set of talks at past. Thank you very much.